AC Verma chapter 26, numerical 21. This is a cylindrical volume V and surrounded by adiabatic walls, and there is a fixed diathermic valve. Fixed diathermic valve. The total volume is V. The valve separates it in two equal parts. Therefore, volume of the right side is V by 2, volume of the left side is V by 2. Initial pressure and temperature P1 T1, final pressure and temperature P2 T2. This is given that this is the internal energy of the gas. Now, it is kept for a long time, and first of all you have to find out the work done by the system. The work done, the question is find out the work done by the gas on the left part. Now we know that work done dW is equal to PdV. As this separator is fixed, it cannot move, therefore volume remains fixed. V is equal to constant. As the boundary, separating boundary is fixed, therefore dV is equal to 0, therefore dW is equal to 0. So the work done on the left part is 0. This is the answer of the first part. Now in the second part you are asked to find out the final pressure of the two sides, that is the right side and left side, and the final temperature. Let us consider after a long time the pressure of the right side become P2 dash, temperature becomes T, and volume is V by 2 as this one is fixed, and the pressure on the left side is P1 dash, temperature is constant as this wall is diathermic and heat can flow from one side to another, therefore temperature changes and they attain a final temperature which is T and the volume is V by 2. Now in this problem you have to find out P1 dash, that is final pressure, P2 dash, that is final pressure of the other chamber, and the common temperature, final temperature attained by them. Number of moles remain conserved. Let N1 mole of gas was here and N2 here. Therefore, we can write from this initially N1 is equal to, we know that PV is equal to nRT. Therefore, N1 is equal to P1 V by 2 R T1, and N2 is equal to P2 V by 2 R T2. Now, finally, here the number of mole N1 is equal to P1 dash V by 2 R T, and N2 number of mole here is equal to P2 dash V by 2 R T. As number of moles in the right side as well as in the left side remain same, we can see from these two equations this T1V by 2R T1 is equal to this P1 dash V 2R T, but T is the final temperature. V by 2R, V by 2R cancels, therefore P1 dash, that is final pressure at this chamber, will be P1 T by T1. Now we have to find out common final temperature T. That one is a separate process, and similarly from these two we can write that P2 dash equating these two is equal to P2 T by T2. Therefore, these are the final pressures of this chamber and this chamber. But here we have to find out the final temperature, and then we can put the value of the temperature here to get the final expression. Now, how to find out the final temperature? To find out the final temperature, let us write T1 dash is equal to T1T by T1 and P2 dash is equal to T2T by T2. Now, the internal energy of this chamber and this chamber changes obviously as the temperature changes. Heat flows from this side to this side, therefore temperature changes and internal energy changes, but the total internal energy remains constant, as no heat can go outside the system, as these separators or boundary is adiabatic boundary. Therefore, we can say that initial internal energy of this chamber and this chamber is equal to final internal energy of this chamber and the right chamber. Therefore, initial internal energy, you can put this expression 1.5 N1 R T1 plus 1.5 N2 R T2 is equal to final internal energy, that is 1.5 N1 RT plus 1.5 N2 RT. We know the values of N1 and N2. You can put here 1.5 R cancels. Therefore, we can write N1 T1 plus N2 T2 is equal to N1 plus N2 into T. N1 number of moles equal to P1V by 2 R T1, as this volume is V by 2 into T1. N2 number of moles in this chamber P2V by 2 R T2, this volume is V by 2 into T2 is equal to N1 plus N2 into T. T1 cancels this. Therefore, here we have to put N1 and N2. P1 V by 2 R T1 plus P2 V by 2 R T2 into T. V by 2R, V by 2R, V by 2R, all this cancels. Therefore, we get P1 plus P2 is equal to P1 T2 plus P2 T1 by T1 T2 into T. And from this we can find out the final temperature, which gives us the expression T is equal to P1 plus P2 into T1 T2 by P1 T2 plus P2 T1 plus P2 T1. This is the answer of the part C, which is the final temperature of this chamber. The final temperature of this cylindrical chamber is P1 plus P2 T1 T2 divided by P1 T2 plus P2 T1. We arrive here from this one. Now you can put this final temperature to find out the final expression of the pressures of these two chambers. Therefore, P1 dash, that is equal to P1 by T1 into T, that is P1 plus T2, T1 T2 divided by, we can write this as a constant, T1 T2 plus T2 T1. T1 T1 cancels, therefore T1 T2, P1 plus P2 divided by P1 T2 plus P2 T1. This is the final temperature of the left chamber. Now you can find out the final temperature of the right chamber. Similarly, putting the value of T here, it will be P2 dash is equal to P2 T1, P1 plus P2 by P1 T2 plus P2 T1. Therefore, this is the answers of the part B. We can find out the final pressures from these two expressions and the final temperature. This is the answer of part C. Now the last part of the question, you are asked to find out how much heat has been flown from the gas on the right to the gas on the left. You have to find out the amount of heat that flows from to the gas on the right, from the gas to on the gas on the right to the gas on the left. Okay, right to left. Therefore, T2 is greater than T1, and how much heat dQ? We have to find out dQ. Now, from first law, we know that dQ is equal to du plus dW. Here, dW is 0, the answer of our part A. Therefore, we can write it that dQ is equal to du. We can write it dQ is equal to du. Therefore, we have to find out the amount of the change in internal energy of this part. The change in internal energy of this part. So this is the initial internal energy, that is 1.5 N1 R T2 minus, N2 R T2, number of moles is N2 here, minus final internal energy 1.5 N2 R T. This. The expression of internal energy is given in the question, 1.5 nRT. Here the number of mole is N2, the temperature initial value is T2 and final value is T. Now we have to put the values of N2 and T and calculate it to find out the amount of heat that flows from this one to this side. Now 1.5 N2 R T2 minus T. You can always put the value of N2, that is 1.5. N2 is, this volume is V by 2. I have written this already. P2 V by 2 R T2. T2 minus T. We know the expression of final temperature. The expression for the final temperature. Now put it that this is T1 T2 P1 plus P2 divided by P1 T2 plus P2 T1. This was the expression of final temperature of the system. Now we have to calculate this to find out the final answer. This is equal to 1.5 P2V by 2R T2 P1 T2 plus P2 T1 P1 T2 square plus P2 T1 T2 minus P1 T1 T2 minus P2 T1 T2. This term P2 T1 T2 cancels. Therefore, we can write this Here dq is equal to 1.5 P2V by 2R T2. P1 T2 T2 minus T1 T2 minus T1 divided by P1 T2 plus P2 T1. You can take this part as a constant which is lambda. Therefore, P1 T2 plus P2 T1 is equal to lambda. You can put this. Now, T2 T2 cancels. Therefore, this is 1.5 means 3 by 4. 3 by 4 T1 T2 V by R T2 minus T1 P1 T2 plus P2 T1. This is the amount of heat that flows from the left side to right side.